Hey class, this is going to be your 7-7 video. So 7-7 is all about fundamental matrices, which is not really a new concept. A fundamental matrix is going to be the same matrix that we took the determinant of to calculate the Wronskian. So let's go ahead and define that quickly. If we consider the system we've been considering, so we have x prime, that's vector x prime, equals a possibly non-constant, although again we're going to do this always for constant coefficients. This theorem just happens to be true even if it's not. X prime equals a of t x. If we have x1, x2, and so on up to xn, which form a fundamental set of solutions for, I should have labeled it, for star. Ooh, blurry. Hang on. Let's get that into focus. Come on. That's not working. Let's try again. Maybe slightly better. Probably not. If I keep writing, there we go. It should come into focus. All right. Let's see. On an interval, usually our interval is the whole real line, just like we've been doing, or maybe 0 to infinity sometimes. Then the matrix, and we're going to use a cap psi here of t, which is just the matrix made up of by your fundamental set of solutions. Just put your vectors into your matrix. So like I said, or I haven't said that yet today, our vectors have tended to be two-dimensional vectors because we've been doing 2x2 systems, but you could have n be a larger number. All right, so the matrix psi, whose columns are the vectors in the fundamental set of solutions, is called a fundamental matrix. I like it when things are named in a way that makes sense. 4 star on our interval, because our solutions were only defined on that interval, not perhaps. So if you already had your solutions, writing a fundamental matrix is really no big deal. You just slap them in there, and we can do that. Let's see. So in 7.5, we had x1 equals 1 e to the t, and x2 equals 1 3 e to the minus t, is a fundamental set of solutions for x prime equals, our matrix there was 2, -1, 3, -2, x. So a fundamental matrix for this is going to be psi of t equals, so if I take this guy and I put him in just a single column vector form, he'll be e to the t, just multiplying that e to the tn. And if I multiply this e to the minus tn, I get e to the minus t, 3e to the minus t. So that's, sometimes it's that simple. You have your solutions already, they just ask for a fundamental matrix and you just write it that way. So in 7.6 we solved, we had x1 equals e to the minus t 2 cosine 2t minus 2 sine 2t cosine 2t. And we had x2 was e to the minus t 2 cosine 2t plus 2 sine 2t sine 2t. And that was a fundamental set of solutions for x prime equals 1, negative 8, 1, negative 3, x. And so in this case, our psi is going to be e to the negative t times 2 cosine 2t minus 2 sine 2t. You just got to make your matrix bigger. E to the minus t times 2 cosine 2t plus 2 sine 2t cosine 2t sine 2t. So distribute the e to the negative t into that vector, and that's this column. Distribute the e to the negative t, distribute it in, and then that's this column. So the other thing we can do with these, or another thing we can do, is it turns out that psi of t is also a solution of x prime equals a x. We can plug it in. So let's see. Let's go ahead and do that with the first one from the previous slide. So if we have psi of t equals e to the t, e to the t, e to the minus t, 3e to the minus t, and our system was x prime equals 2, negative 1, 3, negative 2, x. So psi prime of t is equal to e to the t minus e to the minus t, e to the t, and minus 3 e to the minus t. And a times psi is equal to 2, negative 1, 3, negative 2, e to the t, e to the minus t, 3e to the minus t here. And so our first position there is row 1 times column 1, so that's 2 minus 1 e to the t, that's e to the t. And this position here is 3 times e to the t minus 2 e to the t, so that's also e to the t. And then this position is going to be 2 e to the minus t minus 3 e to the minus t, so that's minus e to the minus t. And finally, to get this position down here, we take the second row times the second column, and we get 3e to the minus t minus 6e to the minus t, which is minus 3e to the minus t. And you see these two things are equal, so psi satisfies the equation x prime equals ax. And that's going to be true in general. Another fact is that if psi is a fundamental matrix for x prime equals ax, oops, just ax, not ax prime, then x equals psi of t times some constant vector is the general solution of the system, where c is just a constant vector, so c1, c2, and if necessary we go down to cn. Now that's not crazy if you think about it. Like let's just do it for a 2x2 system. So psi of t equals x1, x2, so just a little two variable system, then psi of t times c equals x1, x2 times c1, c2, and so that's just c1, x1 plus c2, x2. So that's really just a shell game with writing it as a matrix instead of writing it as a linear combination. All right. Let's go ahead and find a couple of fundamental matrices. So let A equal 2, negative 5, 1, negative 2. We're going to find a fundamental matrix for x prime equals ax. So we need to solve this system. We're going to go ahead and use eigenvalues for this. Remember that x equals k e to the lambda t, where lambda is an eigenvalue and k is the associated eigenvector, will be a solution. So this x will be a solution if, or where, I already had a where there. You get the idea. So that's our goals. So we need to go ahead and find our eigenvalues. So we take the determinant of a minus lambda I, and we're going to set that equal to 0. And in this case, that's going to be 2 minus lambda negative 5, 1 negative 2 minus lambda. So that's 2 minus lambda times negative 2 minus lambda minus negative 5 times 1. Just writing that out, that's going to give us lambda squared plus 1. So we have lambda squared plus 1 equals 0. This tells me lambda equals plus or minus I. So remember, when we have complex eigenvalues, we can just take whichever one we want. So we'll take lambda equals I, in which case from this we'll get a k. We'll get k equals, we got to actually do the matrix now, don't we? So plugging that in, we get 2 minus I negative 5, 1 negative 2 minus I. So that will row reduce to 1, negative 2 minus I, 0, 0. Remember, I'm skipping all of the steps. I'm not actually row reducing this. I know what it row reduces to because I know that since the determinant is 0, these rows are dependent on one another. So either one of these rows represents the whole thing. I take the easiest one. So in this case, I get k equals 2 plus I, 1. That's the easiest combination of 1 and negative 2 minus I that I can think of. So that's my k. So then x equals k e to the lambda t, and that's going to be equal to 2 plus I, 1, e to the I t. So now we write that out as in the real part and the imaginary part. So that's 2, 1 plus I times 1, 0 from my k. And e to the it is cosine t plus I sine t. We're looking for the real part and the imaginary part of this x. Those will be our solutions. So I'm just going to FOIL it out. I get 2, 1 cosine t. If I do the last, I'll get minus 1, 0 sine t. And then I'll do the outer and the inner. I guess I'll do inner first to keep the cosine. So then plus I times 1, 0 cosine t. And then plus I times 2, 1 sine t. Let me go ahead and keep those handy. So then x1 is the real part of that x, and so that's 2, 1 cosine t minus 1, 0 sine t. We can write that as 2 cosine t minus sine t cosine t. And then x2 is the imaginary part of that x. So that is just, remember the imaginary part doesn't have the I with it anymore. It's just the coefficient of I. So 1, 0 cosine t plus 2, 1 sine t. And so that is cosine t plus 2 sine t, and then sine t. And so our psi, our fundamental matrix, is just the matrix of those two solutions. So I'll take x1 first. 2 cosine t minus sine t, cosine t, and then cosine t plus 2 sine t, sine t. So that is my fundamental matrix for this system. And we can write then the general solution as we can write the general solution as we'll call it x. X of t equals psi times c. So we can write this as, I don't want to rewrite all that, but I will. 2 cosine t minus sine t, cosine t plus 2 sine t, cosine t sine t, times c1 C2. And that would be the general solution for this system. We can also do initial value problems with these. So if we use the same matrix, suppose we want a solution to x prime equals same a, x, but we want psi to be, sorry, not psi of t, psi of 0 to be equal to, let's say, the identity matrix. So in this case, we can take our solution. I'm going to put it right back here for us. We can take our solution and we want to find so remember, psi of t is also a solution, and so we want I did not write that correctly. Let's see. Psi of t is a solution. Psi of t times c is the general solution for our vectors, but if we want to find the particular psi that, how do I say that? Let's say we want to find, come up with another, how about phi of t, such that phi of t, cap phi of t, prime equals a times phi, and there's our initial value problem. Phi of 0 is the identity matrix. There we go. So we know that psi of t equals, I'm going to write it a third time here, 2 cosine t minus sine t, cosine t plus 2 sine t, cosine t sine t is a solution of that, but we want the one with that satisfies this initial condition. So in this case, what we can do is, instead of multiplying by a constant vector, we can multiply by a constant matrix. So we'll say phi equals psi, phi of t equals psi of t times c. Now, you got to keep in mind that multiplying by constants does not change the fact that this is a solution, right? We have a linear first order system, so I can multiply by a constant, and that is still a solution. What we want to know, though, is which constants do we want, and we want the property that phi of 0 is the identity matrix, but that's going to be equal to psi of 0 times c. This means that c is psi inverse, really psi of 0 inverse. So psi of 0 is just 2, 1, 1, 0, and so c is psi of 0 inverse, and that, let's see, the determinant of this is -1, so that's 1 over -1, and then I switch these two and I negate these two, and then I multiply back in my -1, and I get 0, 1, 1, -2. So that is my particular c that I need. So then the phi that satisfies this initial value problem is equal to 2 cosine t minus, this is just my c again, minus sine t cosine t plus 2 sine t cosine t sine t times the constant matrix 0, 1, 1, negative 2. When we do that multiplication, we're going to get, let's see, cosine t plus 2 sine t, negative 5 sine t, sine t, and cosine t minus 2 sine t. So this matrix here satisfies the differential equation, that differential equation there, and when I plug in 0, I get 1, 0, 0, 1. So it satisfies the initial condition as well. There is a little bit more in this section about how you can have an exponential function with a matrix in the argument, but it requires more series than we typically do. So I think it's interesting, and if you like infinite series, definitely read it, but we will not cover it. I took it out of the homework. I had originally said number 16 was in the homework, and then I double checked, and that's one of these problems. So I've removed that from the homework assignment and definitely won't be on the test, but it is interesting the way we can use power series in order to define an exponential with a matrix for an argument. But, maybe another time. Have a good one, guys.